In this video, we're going to continue talking about titrations of solutions of weak acids and weak bases. And we're going to talk a little more specifically about using pH curves to help us determine the equivalence point. So here's the titration we were working on the last time, right? We figured out that we would need 50 milliliters of our sodium hydroxide solution to reach the equivalence point. And that when we reach the equivalence point, the pH would be 8.60, right? That's all fine information, right? But remember, right, we knew our concentration of acetic acid at the beginning, right? And we knew our concentration of sodium hydroxide. But when we're doing a titration, the point is we know the concentration of one thing. In this case, we'll say we know the concentration of our sodium hydroxide, our titrant, and we're trying to find the concentration of an unknown solution of acetic acid, right? What would that work, and how could we do that using this kind of format where our final pH is something other than 7.0 because we're titrating a weak acid instead of a strong acid? Well, we can do this in part by looking at the titration curve. Right? This represents a titration curve if we're titrating, in this case, 0.1 molar acetic acid with sodium hydroxide, right? And so our variable here is the concentration of sodium hydroxide added. I will admit I simplified this by assuming we had a solution. We're adding solid sodium hydroxide, so the volume of the solution didn't change, right? Just the amount of sodium hydroxide, the number of moles of sodium hydroxide. So this is adding sodium hydroxide to a particular molarity, right? And following the pH. So when we had added no sodium hydroxide, our pH was acidic, about 2.87. And then, right, as we added sodium hydroxide, not much happened for a while, right? The pH didn't change very much as we added more and more sodium hydroxide. And then all of a sudden, as we approached our equivalence point, the pH began to rise quickly across that region, right? And so we can talk about this curve and look at a couple of things, right? So first, right, here early in the curve, right, if we connect those two lines, right, versus if we connect those two lines, we can see that early in the curve, our slope is decreasing, right? The slope is decreasing. But if we go over here, right, we go here to here, right? There our slope is increasing, right? So we go from an area of decreasing slope to an area of increasing slope. Right? And if you've had calculus, you might remember that there is a place between where we make the transition from the slope going down to the slope going up, and we call that an inflection point. Now in this case, our inflection point is at a pH of 4.74, right? Here the pH is equal to the pKa. This is the point where our concentration of hydrogen ions is equal to our Ka. This is the halfway point of our titration. Okay, we have titrated half of our acid, and we have equal concentrations, right, of acid and base, right? At this point, the concentration of our acid form of acetic acid is equal to the concentration of the conjugate base form. So let's clean up our plot, right? Remind ourselves what we have, right? Right here was our first inflection point, right? But then as we went on, we said over here, right, if we connect those 2 points, we get a slope. If we connect 2 points over here, we get a slope. So over here we had an increasing slope. But if we come up here, right, if we connect, those 2 points and those 2 points, now we're back to a decreasing slope, which means between those we have a second inflection point. And that second inflection point, when the pH rises very quickly, right, if we look here, right, there is the concentration of sodium hydroxide added, right? There's the concentration of our original acid, right? This inflection point is our equivalence point. So we can figure out exactly how many milliliters of base or how many moles of base it takes us to get to exactly the inflection point. We can determine our equivalence point, and then we can calculate the concentration of our acid, right? Now, right, the question is, do you have to do a bunch of calculus to get this to work, right? The answer is no, right? But we'll use a couple of principles from calculus in order to explain this. We have a curve here with a continuously changing slope, but we can imagine that there is an equation that describes that curve, right? And so in calculus, one of the things we can do is we can take a derivative of an equation. And what a derivative gives us is a new equation that describes the slope of the original curve at any point. So you get an equation telling you what the slope is anywhere along this curve. Okay? And if we plot that equation, we will get something that looks like this. I'm going to stop and make sure I draw it right, and then I'll come back with it. Right? So there, I've tried to overlay a rough approximation of the equation for the derivative, right? And so we've got, right, a curve. Our slope is getting lower, smaller and smaller and smaller as we approach our inflection point. And then past the inflection point, it starts to go back up. And then all of a sudden, it goes up really fast until we reach our second inflection point. But above that second inflection point, it starts to fall really quickly and comes back down to a slope more like something in here, right? And so on there, right, we're representing our 2 inflection points. I didn't quite hit that one straight, but you know what I mean. And hitting that one, right? Those 2 inflection points are represented on the derivative curve. Now, right, a minimum of something sort of broad like this is hard to evaluate, and hitting the exact maximum here can be hard to evaluate. So is there a mathematical way to make this even easier, right? And so we can take the derivative of the derivative equation and get the second derivative equation, right? And the second derivative is an equation describing how the slope is changing, or how the sign of the slope changes. Okay? So I will try to draw a rough approximation of the second derivative equation on our plot. Okay, so an approximation for our second derivative line would look something like this, right? Our slope is getting smaller, and so, right, our curve is going down a little bit, and it goes down, but at the inflection point, suddenly the change in direction of the slope is positive. So we go from negative to suddenly a positive change in slope, with the point right here representing the inflection point. And where that point crosses the axis, that can be accurately measured. Okay? So then, right, our slope, right, starts getting more positive. Probably should have curved that a little more up, a little more quickly. But as it gets close to the inflection point, the slope reaches a maximum, and then suddenly at the inflection point, the slope goes from changing in a positive direction to changing in a negative direction, right? Again, that second derivative plot crosses the origin at the inflection point. And that crossing can be used to measure accurately where the equivalence point is, right, using a second derivative equation. Now, how do you do this, right? This is one of those things, a lot of us, we don't know the equation for this line. We don't want to do calculus on it. Luckily, right, standard analysis software will do this for us. Right? As a matter of fact, had we been able to do the lab in general chemistry, our Lab Pro software will do this for us. Now, it won't tell us what the inflection point is. We have to read that off the graph ourselves. But an automatic titrator, right? There are automatic titrators where you put your sample in, right? It slowly adds the base, and it evaluates this second derivative plot of the data, and it comes back and tells you where that point is, and then you know where your equivalence point was, and you can calculate back to your original concentration of base, or of the acid, sorry. Okay? So, that's great if you have the software, right? Now, what we'll talk about next is what happens if instead of doing an automatic titration, you want to do a titration with an indicator. That is a compound that changes pH, changes color as the pH changes, right? How do you deal with that with this kind of titration with a variable endpoint? Right? So this plot, right, I went through and calculated, so we're still titrating acetic acid with sodium hydroxide. But what the x-axis is here is the initial concentration of acetic acid, if I could spell initial, right? A little typo there, right? And we're looking at the pH at the equivalence point. And we're starting at 0.02 molar acetic acid and going to 0.12 molar, right? And we can see that, right, the pH really doesn't vary that much. At 0.02 molar, our pH is 8.52. At 0.12 molar, our pH is only 8.91, right? So if that big rise in pH that we saw, right? Remember that curve sort of came over like this and then jumped way up with an equivalence point in here. if that range is between 8.52 and 8.91, that is, if our indicator will change color in that range of pH, then that indicator will work for that titration because, right, there will be very little, that curve is so steep there that there will be very little error in volume, right, depending on what the pH range is, right? And so we can use an indicator, right, to measure a range of concentrations of our acid as long as we can find an indicator whose major increase that changes color at pHs just above the range of our lowest potential concentration and also will catch our highest potential concentration, right? So you have to have an idea of where your endpoints might be, but one indicator can catch them all. All right, so here is a pH indicator chart taken from the textbook TRO, Chemistry and Molecular Approach, the 4th edition. That's the book that we're using for our class, right? And so we saw in the previous slide that our lowest potential concentration of acetic acid that we're looking at changes at 8.52. And if you go back and look at that titration curve, that big jump went up to around 11, right? And so we want an indicator that will change just after 8.52, but that will be done with the change before 11. So if we extend our lines down here, right? Extend our lines down here. It looks like we have, maybe 3 choices. It looks like cresolphthalene maybe starts changing a little too soon to catch our 8.52, right? And so maybe that's not the best. Looks like phenolphthalein does, but phenolphthalein, right? Remember, we need to catch that. The highest concentrations had pHs closer to 9, so some of our solutions won't change until closer to 9. So maybe phenolphthalein would be good for our lowest concentrations of acid, but maybe not for our highest concentrations, right? They might change a little too soon to catch the highest concentrations, sort of leaving us with maybe thymolphthalein that would catch any titration that's finishing between 8.5 and 9 and suddenly jumping to 11, but certainly will be done in that sudden jump to 11. And so maybe thymolphthalein would be the best indicator to use for our titration. So now let's briefly look at the principles behind titration of a weak base with a strong acid. So let's consider, right, the simplest of our weak nitrogen-containing bases, right, ammonia. Right, ammonia can react. Let's titrate it again with something simple. Hydrochloric acid, right, if we're in aqueous solution, right? And the product of that reaction, our product salt, is ammonium chloride. Again, aqueous, right? So our ammonia is aqueous as well, right? Let's just put that in there to be clear. Okay? Now, the question is, what is this titration going to look like? Well, if we go back to our solubility rules, we know that ammonium ion salts are in the same rule with alkali metal salts, and so those are soluble. Chloride ion salts are very soluble with a few exceptions. And so we would expect then that our ammonium chloride in water would dissociate to form ammonium ions plus chloride ions. Again, both aqueous. Right? And so then we have to assess the impact of each of those ions on our solution. Right? So if we go chloride ions and have them interact with water, right? The chloride ions being negative will take the positive, would take the positive part of the water, right? That would make HCl, which is aqueous, plus hydroxide ions if it would go. But again, we know this is a strong acid. And so a strong acid as a reactant will make the reaction complete in the other direction. And so we won't get hydroxide ions. So the chloride ion will have no effect on the pH. Right? Okay. Now, so let's consider our ammonium ion. Right? So our ammonium ion, right? We can think about it in two ways. One, we can think about it in an Arrhenius sense, right? And let me clear this up here, right? If we think about it in an Arrhenius sense, right, it is itself a weak acid. It will set up an equilibrium with ammonia plus hydrogen ions, right? So, right, since there is an equilibrium here, we have to have hydrogen ions to maintain that equilibrium, and so producing those hydrogen ions will affect the pH, right? That is, our equivalence point will be at an acidic pH. Right? We can also look at it as a Bronsted-Lowry process, right? Where we get ammonia aqueous plus hydronium ions, right? But the result is the same, right? We get, because we have an equilibrium, we get a yield of hydronium ions, which makes our solution acidic, okay? So if we're titrating a weak base with a strong acid, our equivalence point will be at a pH less than 7, right? So here we see a titration curve for the titration of, in this case, 0.1 molar ammonia. Sorry, I couldn't make my subscript in my title here, with hydrochloric acid, making the same kind of assumptions we did before, right? We're starting at a very basic, right? This is 11.12 for our pH, right? Now, because we're starting basic, we're going to come down, right? And you can see our slope here is getting greater, or less negative, until we reach our inflection point, right? That is we are half titrated at this point, right? And so that is our inflection point, and that is at pH 9. What was it? 255 approximately, right? So we would get an inflection point here, then our slope would turn more negative again, right? The change in slope would be negative. Our slope would be getting more and more negative. Suddenly we'd reach our second inflection point, right? Our second inflection point, which is, right, note our concentrations, right? That is our equivalence point, right? We would get the same kind of, and then, right, instead of going up, it would go down, and, right, it would get more and more negative, and then it would get less and less negative, right, as we came out of our inflection point. And we could use the second derivative to determine the equivalence point. If we were wanting to use an indicator, the equivalence point pH is 5.13. This next point is 2.70. So we would want an indicator that changes in, below 5.13, but that is done changing before we get down to 2.70. Right? So for this one, we said we want something that changes below 5.13, but is done before we get to 2.7, right? So something in this range, right? So maybe, right, maybe Cresol green starts changing too soon. Maybe the 2,4-dinitrophenol changes too late. But maybe the bromophenol blue is just right, and so we could pick the bromophenol blue. Okay? So that's how we can use either, right, the computer to figure out where our second derivative crosses the origin, or, in this case, a pH indicator to determine, right, when our maximum change in pH is occurring, and that is going to be very close to where the equivalence point occurred. So that finishes our conversation about titrations, right? In the first video, right? In the first video, what was that, 1A, we focused on titrations of weak acids, right? In 1B, we looked at titration curves, and then we extended to titrating weak bases. And in both cases, we talked about using both computer methods and indicators to determine where we find our endpoint.